Hello, this is Jessica Dunn, and we are going to cover Chapter 4 today. Chapter 4 is about the time value of money. The basic premise is that money is not static. A dollar today is not worth the same as a dollar yesterday. In 1920, if you had 430 of today's dollars, you could buy a 2.5 carat princess cut diamond ring and dinner out every night for a year. Today, that same $430 would buy you a 2/10 of a carat round diamond ring, not even including tax. Time value of money is very important because most of our financial decisions concern costs and benefits that occur over time. We're not looking at a cost that occurs simultaneously as a cash inflow. Time value of money allows us to compare cash flows over different time periods. So, for example, time value of money would allow you to determine which is better, $1,000 today or $1,750 in 10 years. Your answer would depend upon what rate of interest you could earn on the money that you receive today. For example, if you deposited that $1,000 today and could earn 12% per year, you would prefer that money be paid today. If you could only earn 5%, you would be better off choosing the $1,750 in 10 years. Suppose a firm has an opportunity to spend $15,000 today on an investment that will return to them $17,000 over the next 5 years. In year 1, they would receive $3,000, year 2, $5,000, year 3, $4,000, year 4, $3,000, and year 5, $2,000. Is this a good investment? To be able to make a determination, managers have to compare these cash flows at a single point in time. So the first thing that we do whenever we're looking at time value of money problems is we put our cash flows on a timeline. So at time period 0, we're going to spend $15,000. We denote a capital expenditure by placing a negative sign in front of it. So a negative $15,000 means that we spent $15,000. In year 1, we received $3,000. That's positive. Year 2, we received $5,000. Year 3, we would receive $4,000, and so on. So we can take cash flows either to backwards in time or forwards in time. If we want to take cash flows forwards in time, we're finding the future value of a stream of cash flows, and that's called compounding. If we're bringing cash flows backwards in time to today's date, that's called discounting. We would be finding the present value of cash flows. Before we can get started working any problems, I want to introduce you to your calculator a little bit. If you have the BA2 Plus, these are the buttons that you're going to be using primarily. So it's the third row, the N, the IY, the PV, the payment, and the future value. N is the number of periods. I is the interest rate. PV is the present value. Payment is the amount of payment. In the beginning here, we're not going to be using the payment button. That comes later on in this chapter. FV is future value. And compute allows you to compute which variable of interest that you're looking at in the particular problem. If you have a graphing calculator, so a TI-83 Plus or anything newer than that, so a graphing calculator, first you need to push the APPS button, APPS. Once you push the APPS button, a screen is going to pop up and you need to enter on the Finance button. That's going to bring up another menu and you push TVM Solver. And then you should see these exact same variables. You'll see N, IY, PV, payment, and future value. At the bottom, you'll also see CY and PY, compounding periods per year and periods per year. In this course, we always leave those at 1. For those of you with a financial calculator, you first need to set it up. Just a little intro, if you ever push the second button, that allows you to access the words above the buttons. So for example, if you pushed second and the up arrow, that would delete. If you pushed second and the natural log button, that would give you the exponential function. So to set up your calculator, we first need to format it. So you push second and the format button. The second button is the dark gray button, and format is the period. You need to set your decimals equal to 9. That's going to give you a floating decimal so you don't get incorrect answers due to rounding. To get out of this menu, you push the second and the quit button. The quit button is also the compute button, the very top. The next thing that you need to do is push second and payment. The second button is the dark gray button. Payment is on that third row right next to future value. You need to make sure that it says end. If it doesn't, you push the second and enter button. If you have a graphing calculator, you don't have to make any of these changes. On the bottom of your time value of money solver, you just need to make sure that your calculator is on end and not beginning. So here I'll go through this. First, we need to push the second and format button. Make sure that decimal equals 9. If it doesn't, you simply push 9 and enter. Now we need to get out of this menu, so second and quit. Now we need to make sure that our calculator is in end mode. So we push second and payment. Ours says end. If it didn't, it would look like this. We would push second and set and change it to beginning and get out of this menu, and now you see at the very top of your screen on the right hand side it says BGN, and that will be there all the time if your calculator is in begin mode, which we don't want except in one particular instance that we'll cover later on in this chapter. So I need to get my calculator back out of begin mode. So second and payment, second and set, and second and quit. So now my calculator is in end mode. So now that we understand what buttons we're going to be using, we can start talking about financial concepts. So the first thing that we're going to discuss is future value. Future value is the value of a cash flow. You find this by applying the idea of compound interest over a specific period of time. So you deposit an amount. That value that you deposited is going to start collecting interest. At the end of each period, the interest is added back to the principal, which is the amount you initially deposited, and becomes a part of the principal. So the interest starts earning interest. And that's the idea of compound interest. Here's an example. If Fred puts $100 in a savings account and it pays 8% interest, the interest is compounded annually. That means the interest is added to the principal every year. How much will he have at the end of 1 year? So he would have, I'll turn my pen back on. Future value would be equal to the $100 that he deposits today times 1 plus 8%. and that's $108. Now, some of you, whenever you're looking at this problem, you may say, well, he deposits $100 and then he's going to earn 8% on that $100. That's exactly what I just wrote. I just factored out the 100. So if we factored out 100, it would be 100 times 1 plus 8%. Exactly what we just wrote. So if Fred were to leave this cash into his account for another year, how much would he have at the end of the second year? So he's depositing $100 today, and it's going to sit into his account for 2 years. At the end of year 1, he has $108. That 108 is now gaining interest, so we need to see how much he'll have at the end of the second year. So we already know that he's going to have 108 at the end of the first year, and we can multiply that by 1 plus 8%, and we'll get $116.64. If we wanted to write this in a more formula style approach, which you'll want to do for problems in this course, notice that 108, we'll bring this equation down, so 100 times 1 plus 8% times 1 plus 8%, that's what we did here. I just substituted this formula in for the $108 down here. Gives you $116.64. And this is the same thing as 100 times 1 plus 8% squared. And all of these give you $116.64. So now that we kind of understand the basics, we can put this into formula. For the formula, we're going to use these inputs. FV is the future value. PV is the present value. R or I, some calculators use R, some calculators use I, some books use R and some books use I, so if you see R or I, they're both the interest rate. And N is the number of periods. So the general equation then, the future value at time period N is equal to the present value times 1 plus the stated rate raised to the nth power, which is what we just did. So Fred had placed $100 at time period 0, so we'll put in our timeline. At time period 0, he deposits $100, and we want to know how much that's worth at the end of 2 years. So we're wanting to know the future value. The present value here is 100. The interest rate, he is earning 8%. And N is the number of periods, and so that's equal to 2. So we can put this into a formula. The future value is equal to the present value of 100 times 1 plus the 8% squared. And that gives you $116.64. So here's another example. Jane puts $800 in a savings account that pays 6% interest compounded annually. She wants to know how much money will be in the account at the end of 5 years. So first, let's put this on a timeline. At time period 0, she's depositing $800 into her account. And we want to know how much that's going to be worth in 5 years. So we're wanting to find the future value. We're taking it forward in time, so we want to know the future value. We're going to be compounding. So we can use our equation. The future value is equal to the present value, the 800, times 1 plus our stated interest rate of 6%, raised to the number of periods, which is 5. And so that's $1,070.58. Instead of using the formulas, which the formulas as we go on throughout this course are going to get more and more complicated, instead of using these formulas, we can use our calculator. The whole purpose of having a financial calculator. So our calculator, remember we have those buttons on the third row, or if you have a graphing calculator, you go through your TVM solver and you can access those. So these buttons right here on the third row, the N, the IY, the PV, the payment, and the future value. These are the same numbers, these are the same variables that we use in our formula. So we can enter these in. Let me write them down first. So we're wanting to know the future value. We know the present value is 800. N is 5. The interest rate is 6. And we're wanting to know the future value. So we can solve for future value now. We just enter these in. First of all, you need to make sure that your time value of money worksheet is cleared. So first we need to make sure that our time value of money is cleared. And to do so, if you have a financial calculator, you push second and clear TVM, which is above the future value button. So second and clear TVM. I didn't push the second button. Clear and TVM. That ensures that every single one of these has a 0 in it. If you have a graphing calculator, all you have to do is put zeros in for the numbers that we aren't using. So, for example, you would make sure that payment is equal to 0. So to get the future value, we know the present value is 800. So we type in 800 and then push the present value button. So now our present value is set at 800. There's no need to push enter. By simply pushing the PV button, you are entering in the $800. The number of periods, N, is 5. So we push 5 and N. Now our number of periods is set at 5. And the interest rate is 6. In a financial calculator or a graphing calculator, you can put interest rates in as whole numbers. You don't have to put in 0.06. You just type in 6. So 6 and the interest rate. So now we're ready to determine what the future value is. So we compute the future value. Again, compute is in the upper left-hand corner. Compute and future value. One interesting thing here to note is that it gives you a negative number. We'll discuss that in just a moment. So the steps that you take here is you type in 800 PV, 5, the N button, 6, and the IY button. Then you push the compute button and future value. And it tells you that the future value is $1,070.58. But the interesting thing is that it gives you a number, a negative number for the future value. It tells you that your future value is a negative $1,070.58. That's just the way your calculator is set up. So generally we put cash outflows as a negative number and cash inflows as a positive number. Because our calculator solves this equation. It's not solving the exact same thing that we are. It says the future value plus the present value times 1 plus the interest rate is raised to the nth power, and they set that equal to 0. So either the future value or the present value is going to have to be negative to cause this equation to equal 0. So the way that we usually think about it is we say, if you deposit $100, that $100 left your pocket, you no longer have access to it. So it would be a negative $100. So in the example that we just did, typically I would just put the present value as a negative. Because he deposited $800 into a savings account, he no longer had access to that money. When he withdraws it in 5 years, he'll have $1,070.58. So that should be a positive number. Now you can choose which one you want, whether or not you want it to be the present value or the future value to be negative. It's completely up to you. But this is the way that I like to think about it. As we get further on in the semester, or in this chapter, it's going to be more and more important to keep your negatives and your positives straight. So here's a picture of compounding. If we deposit $1 today and we leave it in the bank at varying interest rates, this is how much we'll have. You see that this is the idea of compounding. As the periods increase, the money starts to grow at a faster and faster rate. And that's because the interest that your money has earned is now earning interest. So interest is earning interest, the idea of compound interest. So it starts to look like an exponential function. Your money starts to grow at an increasingly fast rate. That's even happening down here at the 5% level. You just have to zoom in more to see it. But it's growing faster and faster each period. So the opposite of future value is present value. If we're taking cash flows backwards in time, we would be finding the present value. The present value is the current dollar value of a future amount. And we find the present value by discounting cash flows, the inverse of compounding interest. And here's an example. Paul has an opportunity to receive $300 in 1 year. If he can earn 6% on his investments, what is the most that he should pay for this opportunity? So at time period 0, he wants to know how much he should pay to receive $300 in 1 year. And the interest rate is 6%. So we know our equation for future value. Future value is equal to the present value times 1 plus the interest rate raised to the nth power. We can rearrange this equation, and we get the present value is equal to the future value divided by 1 plus the interest rate raised to the nth power. So we know the future value is 300. And we divide that by 1 plus our stated interest rate of 6% raised to the first power. And that gives you $283.02. So to have $300 in 1 year, he would be willing to pay up to $283.02. This means that $283.02 is equal to $300 in 1 year. So here's our general equation. The present value is equal to the future value divided by 1 plus the stated rate raised to the nth power. So here's another example. Pam wants to find the present value of $1,700. She will receive that $1,700 in 8 years. Her opportunity cost is 8%. So the discount rate here is 8%. So we can use our equation. We can put it on a timeline first. So time period 0, she's wanting to know what the value is at time period 0, the present value. Of $1,700 that she'll receive in 8 years. So the present value is equal to the future value divided by 1 plus the stated interest rate, 8%, raised to the nth power, the number of years, and that's 8. Now whenever you're entering things in as an equation, you're not using your time value of money calculator, you need to make sure that you are entering your interest rates as 0.08, not just a whole number 8. And so when you work that out, you should get $918.46. For those of you with the financial calculator, just a reminder on how you would enter that in. So first you would do 1 plus your 8% and find what that's equal to. Then you push your y to the x button, which is directly above the number 9, and push 8 and equals. So that gives you your denominator. So it would be 1,700 divided by 1.85093. And you'll get $918.46. So we can use our time value of money calculator as well. We know the inputs. We know that the future value is 1,700, and that would be a positive 1,700 in our calculator terms, because that would be money that we would be receiving in 8 years. Now that means if we put the $1,700 in as positive, when we compute the present value, it's going to come back as a negative, which makes sense in our reasoning because that would be the amount that it would cost to receive $1,700 in 8 years. Now you need to be careful, because if on the exam you typed in a negative $918.46, that would not be correct. It's there for interpretation purposes only. There's no such thing as a negative $918.46, so you would be getting paid that to receive $1,700 in 8 years. It just doesn't make sense. So anyway, the inputs for our calculator, the future value is 1,700. The interest rate is 8%, which we enter in as a whole number. N is 8. And we're wanting to know what the present value is. So we can work this out in our calculator. The first step always is to clear your time value of money. So second and clear TVM above the future value button. Second and clear TVM. So we know the future value. The future value is 1,700. Type in 1,700 and future value. We type in the interest rate, 8%, so 8 and IY. And the number of periods is also 8, so 8 and N. And we need to know what the present value is, so we compute the present value. and it gives you a negative $918.46. Which again, that's for interpretation purposes only. It would cost you $918 to receive $1,700 in 8 years if you're earning 8%. So the present value, $918.46. If you're using a graphing calculator, when you pull up your TVM solver, you should see these same inputs. So it's going to say I may get the order wrong here, I don't have a graphing calculator, IY, PV, future value, and payment. I'm almost certain I have the order wrong. And all you have to do, N would be 8, the interest rate would be 8, again a whole number. We are wanting to find the present value, so we just skip that one. Scroll down to future value and type in 1,700 and make sure that 0 is in for payment. Scroll back up to your present value and you push alpha and enter. And it will solve for the present value for you. And you should get $918.46. So here's a picture of discounting. Remember, it's the inverse of compounding. When we're finding the present value of a sum, it looks exactly the opposite of compounding. We're just below it's just the inverse. So the way our calculator works is we have 5 keys that we can use. As long as we enter 4 of them, we can solve for the 5th. So we can solve for something like the amount of time, which would be N, the number of periods. So let's assume that we invest some amount today, and we want to know how long it's going to take for that amount to double. The main thing that we need to know is the interest rate. And we'll say this would be given in the problem if the interest rate is 20%. So we're wanting to deposit some amount today. The amount that we deposit is arbitrary. It doesn't matter. We're just wanting to know how long it takes to double. So we can say, how long does it take for $1 to turn into $2? So we have our $1, and we're wanting to know how long does it take for that to turn into $2 if our interest rate is 20. Now for calculator purposes, we would put the dollar in as a negative because that's money that we would no longer have access to. So you could use a formula to do this. So you could say future value is equal to present value times 1 plus the interest rate raised to the nth power, and solve for N. Put in the input so we know the future value is $2. $1 times 1 plus the interest rate of 20% and raise that to the nth power and solve for N that way. But you can see that it becomes increasingly difficult to solve for these using formulas when we can so easily do this with our financial calculator. So with our financial calculator, we know the future value is $2. The present value, remember how our calculator works problems, either the present value or the future value is going to have to be negative, so we put cash outflows as negative. So the present value is a -1. And the interest rate is 20%. That's a whole number 20. Again, we're not using payment yet, so payment is 0. And this is exactly what your graphing calculator should look like within the TVM solver as well. You should have these typed in. Then you scroll up to N and push alpha and enter. So the first step, clear your time value of money. So second, and clear TVM. Our future value is 2, so we push 2 in future value. Our present value is a -1, so we push 1 and negative, then present value. Our interest rate is 20, so 20 and IY. A 0 should already be in for our payment because we cleared the time value of money. If you want to make sure, you just push 0 and payment. 0 and payment. And then we solve for N, so we compute N. And you get 3.8 years. So it takes 3.8 years. Just a side note here, the $1 and $2 are arbitrary. You could have just as easily chosen $100 and $200 or $1,000 and $2,000. It doesn't matter. $5 and $10. You would still get 3.8 years. So what if we wanted to solve for the interest rate? If we wanted to invest $1 and it be worth $2 in 3 years, at what rate would we have to earn our money? You could do this problem with, if we wanted to invest $100 and receive $200 in 3 years, what rate would we earn? That's fine. The $1 and $2 again is arbitrary. So we can put this on our timeline. At time period 0, we're wanting to invest $1. Again, that's a cash outflow, so that's a negative. And we're wanting to know at what rate would it require to earn if we wanted to have $2 in 3 years, if we wanted our money to double in 2 years. So again, you could use an equation. The future value is equal to the present value times 1 plus the interest rate raised to the nth power, where the future value is 2 and the present value is 1 times 1 plus r raised to the 3rd power. And you could solve for r. Or you could use your financial calculator. So n is equal to 3. Our present value is a -1. The future value is 2. And the payment is 0. And so we're wanting to solve for IY. So first step is to clear our time value of money. N is 3. The present value is a -1, so we push 1 and then the negative button. Present value. The future value is $2. The payment is 0. And we compute our interest rate. And we get 25.99%. So if we want our money to double in 3 years, we would have to invest it at 25.99%. So up until this point, we haven't used the payment button, but now we're going to start doing that. So we're going to talk about annuities. Annuities are streams of equal periodic cash flows over a specific period of time. These cash flows can be inflows or outflows. So they can either be positive or negative. Ordinary annuities are annuities where the cash flow occurs at the end of the period. So, for example, you pay your credit card bill at the end of the period. You pay your electric bill at the end of the period. You pay your mortgage at the end of the period. Annuities are equal, though, so you would have to be set up on some sort of payment plan for your electric bill to be equal throughout the entire year. An annuity due is an annuity where the cash flow occurs at the beginning of the period. So for example, your rent. You pay your rent on the 1st to live there throughout the month. An annuity due is always greater than an ordinary annuity because the interest gets compounded for one additional period. And so here this is presented on a timeline. The cash flows for an annuity due are occurring at the beginning of the period instead of the end of the period. So we're going to work with this example. Fran is choosing between two annuities. Both are 5-year $1,000 annuities. That means she receives $1,000 every period. Annuity A is an ordinary annuity, and annuity B is an annuity due. This is the equation for an ordinary annuity. The future value is equal to the periodic cash flow times 1 plus the stated rate raised to the nth power minus 1 divided by the interest rate. So you can see why it's important to become familiar with your calculator because these equations are becoming increasingly difficult. So Fran wants to determine how much money she will have at the end of 5 years if she chooses annuity A, the ordinary annuity, and earns 7% annually. So again, the equal periodic cash flow here is $1,000. So we'll put this on a timeline. She's going to receive $1,000 every period for 5 years. So she's going to receive $1,000 here. And she's wanting to know how much that's going to be worth at the end of 5 years. So we know that we need to use the payment button here because each of these cash flows are equal. If the cash flows were not equal, we would not use the payment button. So here, if we want to put this into our financial calculator, we know that N is equal to 5, the number of periods. The interest rate is given, and that's 7. The present value is 0. So as of time period 0, she hasn't put any money anywhere. She hasn't received any money. So at time period 0, it is 0. And now the payment, she's receiving $1,000 every period. So it's $1,000. So we can put this in our calculator. First step is to clear the time value of money. So N is 5. The interest rate is 7. The present value is 0. The payment is $1,000. And we want to know what the future value is. So we compute future value. And we get $5,750.74. So if you had a graphing calculator, it would be the exact same process. You would put each of these in for your time value of money solver, then push alpha and enter on the future value. So we can find the present value. We just found the future value. We can also find the present value. Again, the calculations by equation get increasingly difficult. The cash flow, this is also the payment. So the payment divided by the interest rate times 1 minus 1 divided by 1 plus the stated rate raised to the nth power. And here's the example. Braden Company wants to determine the most it should pay to purchase a particular annuity. The annuity is going to return $700 at the end of each year for 5 years. The required return is 8%. So we know that this is an ordinary annuity because it says at the end of each year. So we can put this on a cash flow timeline. It's going to return $700 a year for 5 years. And we're wanting to know how much they should be willing to pay for this investment that will return $700 a year for 5 years. So you could find the present value of each of these cash flows individually and add them up. Or you could use the payment button on your financial calculator. So N is 5. The interest rate is 8. The future value is 0. At the end of the period, when this project is done, there's not going to be any cash flows left over that will be returned to the company. And the payment, it's going to return to the company $700 every period. And they want to know how much they should pay for this investment, or what is the most that they're willing to pay. So first step is to clear our time value of money. Okay, I had a student come in. The first step here is to clear the time value of money. So N is 5. The interest rate is 8. The future value is 0. And the payment is $700. So we compute the present value. And you get $2,794.90. Again, a negative sign makes sense because that would be how much you'd be willing to pay to receive $700 a year. But if you were putting this in for an answer, you should put in a positive because it doesn't make sense to say that you're paying a negative $2,700. So the present value, $2,794.90. So now we can talk about an annuity due. An annuity due is where the cash flows occur at the beginning of the period. And here's the formula. The future value is equal to the cash flow or the payment times 1 plus the stated rate raised to the nth power minus 1 divided by the interest rate. All of that times by 1 plus the interest rate. So Fran is now wanting to calculate the future value of the annuity due, which is the annuity B. So before you can work this problem, you have to turn your calculator into begin mode. Remember when we were setting your calculator up and we went through the form and we went through the second payment button to make sure that it said end? This is the only instance where you will ever want it to say begin. Once you've put it in begin mode, there should be a BGN in the upper right hand corner. If you have a graphing calculator, all you have to do at the bottom of your TVM solver is push enter when your cursor is on top of the begin. And so here's the steps. They're written on the slide. So second and payment. So it says end and we want it to say begin. It tells you in the top of your calculator in the center, it has the set button, which means that's what you need to push to be able to switch it to a different mode. So we push second and set, and that is the above the enter button. So now it says begin. To get out of this, you have to push second and quit. So now our calculator is in begin mode. We know this because it has a BGN in the upper right hand corner. So we can put this in our calculator now. Now that we have it in begin mode, we enter it in exactly the same way as we did the ordinary annuity. Oh, turn my pen back on. So the present value is 0. We're wanting to calculate the future value. N is 5. The interest rate here, we're going to assume is the same interest rate, which was 7. And the payment is $1,000. So the first step, we clear our time value of money. Second, and clear TVM. The present value is 0. N is 5. The interest rate is 7. The payment is $1,000. And we're wanting to compute the future value. $6,153.29. $6,153.29. Alternatively, we can calculate the present value. If it's an annuity due, we need to make sure that our calculator is in begin mode. It's equal, if we were using a formula, it would be equal to the cash flow divided by R. Cash flow in the formula is the same thing as payment, times 1 minus 1 divided by 1 plus the interest rate raised to the nth power, times 1 plus the interest rate. So Braden Company wants to determine the most it should pay to purchase a particular annuity. The annuity consists of cash flows of $700 at the beginning of each year for 5 years, and the required return is 8%. So we know that this is an annuity due because the problem says beginning. So if this is an annuity due, we need to make sure that our calculator is in begin mode. When you're done working an annuity due problem, you should always immediately switch your calculator back to end mode so that you don't accidentally work problems with the in begin mode, because you'll get every answer incorrect. So we've already drawn the timeline for the ordinary annuity. So we can just enter this in. Now that we have it in begin mode, we treat this just as if it were an ordinary annuity problem. So N is equal to 5. The interest rate is equal to 8. We're wanting to know how much they should pay, so we're wanting to know the present value. The future value is 0. And the payment is $700. So our calculator, first step, clear time value of money. And we see that our calculator is already in begin mode. If it weren't, you would push second and payment, second and set, and second and quit. Set is located above the enter button, and quit is located above the compute button. So N is 5, the interest rate is 8, the future value is 0, and the payment is $700. And we want to compute the present value. We get $3,018.49. We're willing to pay $3,018.49 to receive $700 a year for 5 years. The next concept we're going to cover is a perpetuity. A perpetuity is an annuity with an infinite life. So it's continual equal cash flows. So the present value of a perpetuity is equal to the cash flow or payment divided by the interest rate. This is the only time that we don't use the financial calculator. We simply use the formula. So when you're using the formula to calculate a perpetuity value, the present value of a perpetuity, and you're entering in your interest rate, you have to enter it in decimal points. So here's an example. Ross wants to endow a chair in finance. It requires $200,000 a year to support the chair, and they could earn 10% on the endowment. So we have to determine how much he has to invest now, how much he has to give the university now, if they can earn 10% and are going to withdraw $200,000 a year forever. So the present value would be equal to the $200,000 per year payment divided by our interest rate of 10%. Again, you have to put this in decimal points. You can't enter a whole number. And you get $2 million. So if Ross donated $2 million to the university and they earn 10% on the investment every year, that means that they would earn $200,000 in interest every year that they could withdraw to support the chair. They would never touch the principal. They would only withdraw the interest every year. So what if cash flows aren't constant? What if we have mixed streams of cash flows, which in real life is much more practical? So at the end of year 1, this company is going to receive $11,500. At the end of year 2, $14,000. At the end of year 3, $12,900. At the end of year 4, $16,000, and at the end of year 5, $18,000. If the firm expects to earn 8% on their investments, how much would they have by the end of year 5 if they invest these cash flows when they are received? So one alternative is to take the future value of each of these cash flows independently and then add them together. So the future value of $11,500 for 4 years would be $15,645.62. The future value of $14,000 deposited for 3 years is $17,635.97. And you can continue this for each cash flow and then add them together. And you would find that the future value of this stream of cash flows is $83,608.15. We don't have to do this. You don't have to take the cash flows independently. We can put it in our calculator. We're going to cover that in just a moment. So what if we wanted to find the present value of a mixed stream? They can receive each of these cash flows every year, and they want to know how much this investment would be worth. So at time period 1, they could receive $400. Time period 2, $800. Time period 3, $500. Time period 4, $400. And time period 5, they would receive $300. How much are they willing to pay for this investment? To determine this, you would have to take the present value of each of these cash flows independently. So you take the present value of each of these all the way back to time period 0 and then add them up. So $400 discounted back 1 year, $366 and some change. $800 discounted back 2 years is $673 and change. $500 discounted back 3 years, $386. And we can continue this process and add them all up. At the end, if we added all of them up, we would find the present value is $1,904.75. But our calculator does offer a cash flow register. And here's the buttons that you would need to use. So if you have a financial calculator, your directions are on the left. And if you have a graphing calculator, your directions are on the right. So for a graphing calculator, we'll cover that one first. For a financial calculator, we'll cover that one first. We need to get our calculator out of begin mode. To do so, we push second and payment, second and enter, and second and quit. Now the begin sign is gone in the upper right hand corner and we're ready to start. Clear our time value of money. So to do this, we push the cash flow button. Now your cash flow register may already have numbers in it. To clear it, you push second and clear work. Now your cash flow register has to be open for the clear work button to work. So you have to push cash flow and then second and clear work. Just pushing second and clear work without the cash flow register open will not empty it out. So our cash flow at time period 0. Well, here, let me draw the timeline first. Well, I guess we just did that on the previous slide. So our cash flow at time period 0 is 0. So push 0, enter, and the down arrow. And now it says C01. It's wanting to know our cash flow at time period 1. Our cash flow at time period 1 is 400. So we enter in 400, enter, and the down arrow. Now it says F01. That's the frequency of cash flow 1. So it's wanting to know how many times is the first cash flow repeated. If you aren't comfortable using frequency buttons, you don't have to. You could enter in each of the cash flows individually. In this example, there's no reason to use frequencies at all because each of the cash flows only occur once. But if you're not comfortable using it, you just simply push the down arrow and skip that option. So cash flow at time period 2 is 800. Enter and the down arrow, and we can skip the frequency. So cash flow at time period 3 is 500. Enter, down arrow twice. Cash flow at time period 4 is 400. Enter, and the down arrow twice. And the cash flow at time period 5 is 300. Enter. So now that we've entered all of our cash flows, you push the NPV button, which is right next door to the cash flow button. So you push NPV, and you enter in your interest rate. Our interest rate on this example was 9%. Again, you just enter that in as a whole number. So 9 and enter, the down arrow, and compute. You get $1,904.76. So the same answer either way. So here we put what we put in for our calculator for the financial calculator. C01 was 400. Enter. Down. I'm sorry. First we start with let me start over here. We push the cash flow button. Ask for your cash flow at time period 0, which was 0. Cash flow at time period 1 is equal to 400. Enter. And the down arrow twice. Cash flow at time period 2 is 800. Enter. And the down arrow twice. And you continue until you've entered in all of the cash flows. Then you push the NPV button. Your interest rate is equal to 9. Enter. And the down arrow. The enters are important. If you don't push the enter button, It won't save what you entered. Then it pops up, it says NPV, and you push compute. And you get the present value is $1,904.76. If you have a graphing calculator, the steps are much more simple. So you push the Apps button, select Finance, and scroll down until you see NPV. Push Enter when your cursor is on top of the NPV button. And you're going to enter in first your interest rate as a whole number, so 9, comma, your cash flow at time period 0, which is 0, comma, and you have to enter in the commas, then braces, and you enter in your cash flows separated by commas. So 400, comma 800, comma 500, comma 400, comma 300, close braces, close parentheses, and enter. And you should get the same answer. So the full way that the NPV button works, if you are familiar with it and wanted to use frequencies, so NPV, you enter in your rate, cash flow at time period 0, braces, cash flows separated by commas, comma, braces, frequencies separated by commas. So F01, F02, etc. Close braces, close parentheses. So it would be CF1, C02, C03, so on and so forth, close braces. Then comma and frequencies. But frequencies are not necessary. It just saves you a little bit of typing in time. So what is the present value of this uneven cash flow stream? You could take the present value of each one individually. So $90.91, $247.93, $225.39, and a negative $34.15, and that gives you $530.08. So the present value of this stream is $530.08. Or we could put it in our calculator. So first you have to push, if you're wanting to clear out your cash flow register, first you push CF. So we push CF and second and clear work. And we input our cash flows. So our first cash flow at time period 0 was 0. Enter and the down arrow. Cash flow at time period 1 was 100. Enter and the down arrow twice. Cash flow at time period 2 is 300. Enter and the down arrow twice. Cash flow at time period 3 is 300. Enter and the down arrow twice. Cash flow at time period 4 is a negative 50. So 50, negative, and enter. You push the NPV button, enter in the discount rate. Here that was 10%. Enter, down arrow, and compute. And you get the same answer, $530.08. Well, 9 cents. The other one didn't round correctly. So here are your keystrokes. You push CF. Cash flow at time period 0 is 0. Enter the down arrow. Cash flow at time period 1 was $100. Enter and the down arrow twice. Cash flow at time period 2 was 300. Enter and the down arrow twice. Now here's an example where you could use frequency. You could put cash flow 2 as 300 with a frequency of 2, and then cash flow 3 would be the negative 50, or you could skip the frequencies, enter in cash flow 3 of 300, enter down arrow twice, and cash flow 4 is a negative 50, enter. NPV, IY equals 10, enter, down arrow, and compute. If you have a graphing calculator, first you would push your apps button. You'll push your apps button, your finance button, and scroll down to NPV and push enter. First you enter in your discount rate, which is 10, comma, your cash flow at time period 0 is 0, comma, braces, 100, comma, 300, comma, 300, comma, negative 50. Enter, and you'll get the same answer. If you wanted to use frequencies with your graphing calculator, it would be NPV 10, comma, 0, comma, braces, 100, comma, 300, comma, negative 50, comma, braces. The frequency of the $100 is once, the frequency of the $300 is twice, and the frequency of the negative 50 is 1. Close braces, close parentheses. So interest can be compounded more frequently than annually. If you compound interest more frequently than once per year, that results in a higher effective rate because you're earning interest on your interest more frequently. The interest is being added to the principal more frequently than once per year. As a result, that causes the effective rate to be greater than the nominal rate. So the nominal is the stated rate. So it's the amount that would be stated in a contract. It's the amount that's stated in a problem. It's the rate that we actually use when doing calculations. The effective rate is the rate that you actually earn. And these two are only different if we have compounding more frequently than annually. So if we have semi-annual compounding or quarterly compounding or anything narrower than that, the effective rate is going to differ from the nominal rate. So here we can see this. We're investing $800 at 8%. And it's being compounded semi-annually. So semi-annually means that it's going to be calculated the interest is going to be added to the principal every 6 months. So we compare semi-annual compounding to quarterly compounding. Remember whenever we did this problem at the beginning of the lecture and we said $100 deposited 8% interest compounded annually for 2 years was $116.64. Now we're looking at it being compounded semi-annually, so twice per year, every 6 months. So here we see that instead of it being worth $116.64, it is worth $116.99 at the end of the 2 years. And that's because the interest is being added to the principal more frequently, which causes the future value to be higher because it is growing interest that much more quickly. So here quarterly, the interest is being added to the principal 4 times per year. And here we see that instead of the future value being $116.99 is now $117.17. So more frequent compounding is going to cause our money to grow more quickly. So the general equation for interest compounding more frequently than annually is given here. So the future value is equal to the present value times 1 plus the interest rate divided by the number of compounding periods per year raised to the number of compounding periods per year times the number of years. So M, compounding periods, and N is number of years. So if we were looking at semi-annual, N would be 2. If we're looking at quarterly, N would be 4. Monthly, N would be 12. So it's the number of compounding periods within the year, and N is the number of years. So if we were to do the Fred Moreno example using semi-annual compounding, remember this was deposit $100 for 2 years at 8%. How much is this worth at the end of the 2 years? So here the future value would be equal to the present value, the amount deposited, times 1 plus the stated rate divided by the number of compounding periods. We're saying semi-annual here. If it's semi-annual, M is equal to 2. Raise that to the number of compounding periods, which is 2, and multiply it by the number of years, which is 2. So if you work this out, you get $116.99, which is what we found on the previous slide. So we can do this in our calculator as well, but there are some modifications that you need to make. So if you were to put this in your calculator, the present value would be the $100. Oh, 100, not 1,000. N, the number of periods, would be equal to M times N. So the number of compounding periods times the number of years. So it would be 2 times 2, which is 4. And the interest rate that you would enter would be the stated rate divided by the number of compounding periods per year. So that would be 8 divided by 2, and you would get 4. So you can enter these into your calculator. Again, the payment is 0, and we're solving for the future value. So the first step is to clear our time value of money. Second, clear TVM. We want to enter in the present value of 100. N is 4. The interest rate is 4. The payment is 0. And we're wanting to compute the future value. And you get $116.99. So what if we did that same example, but we said quarterly compounding? So in quarterly compounding, M is equal to 4. This is still looking at $100 at 8% for 2 years. We're wanting to know the future value of this. So N would be 2. So we could use the equation 100 times 1 plus the stated rate, 8%, divided by 2, times number of compounding periods per year. I'm sorry. Let me go back. 8% divided by the number of compounding periods. This is quarterly, not semi-annually, so that would be 4. We raise that to the number of compounding periods per year, which is 4, and multiply it by the number of years, 2. If you work this out, you get $117.17. Alternatively, you can do this in your calculator. So the present value we leave alone, it's $100. N, the number of periods, is now equal to M times N. Compounding periods times number of years. That's 4 times 2, which is 8. And the interest is the stated rate divided by the number of compounding periods per year, so 8 over 4, which is 2. The payment is 0, and we're wanting to solve for the future value. So first step is to clear the time value of money. Present value is 100. N is 8. The interest rate is 2. The payment is 0. And we're computing the future value. And you get $117.17. So what if interest is compounded continuously? So interest is compounded an infinite number of times per year. To calculate the future value of continuous compounding, that's equal to the present value times the exponential function raised to the stated interest rate times n. So here we have no buttons on our calculator that will make this work either. So if Fred deposited this $100 for 2 years, or for 2 years at 8%, with continuous compounding, how much would he have? So the number of years is 2. Remember the equation? The future value is equal to the present value times the exponential function raised to the stated rate times n. So here for this equation, remember we can't put it into our calculator. There's no time value of money worksheet for this to work. So our interest rate would be 8%, and PV would be 100. So the future value would be $100 times the exponential function raised to 8%. Because we're not using our TVM solver, we have to put that in as 0.08 times 2. So if we're putting this into our calculator, the steps that we would take is we would put in 0.0 if you have a financial calculator. If you have a graphing calculator, you can type it in exactly the way it looks and it'll work. But if you don't, you would type in 0.08 times 2 equals, that would be 0.16. Then you need to push the second button and the e to the x button, which is above the natural log button. And that will give you 1.1735, and you multiply that by 100 to give you $117.35. And I'll show you. So you do your interest rate, 0.08 times 2, that equals 0.16. So you push second and the natural log button, and that tells you that the exponential function raised to 0.16 is 1.1735, and now you multiply that by 100. So it's $117.35. So if you're wanting to convert between nominal and effective rates, if you're wanting to know actually how much you're earning or paying as compared to the amount that's stated in a contract, this is the equation that you use. The effective rate is equal to 1 plus the stated rate divided by the number of compounding periods per year raised to the number of compounding periods per year minus 1. The effective rate is greater than the nominal rate whenever compounding occurs more than once per year. So here's an example. Fred wants to know his effective rate if he has an 8% nominal rate. So in his contract it says that he's earning 8%. He wants to know exactly how much he is earning when interest is compounded annually, semi-annually, and quarterly. So the effective rate, EFF or EAR, is equal to the effective rate is equal to 1 plus the stated rate divided by the number of compounding periods per year raised to the number of compounding periods per year minus 1. So here if we're looking at annually, the effective rate is equal to 1 plus the stated rate divided by the number of compounding periods per year raised to the number of compounding periods per year minus 1. So it's 8%. Anytime the interest is compounded annually, where m is equal to 1, the effective rate and the nominal rate are equal to one another. So m equals 2. The effective rate would be equal to 1 plus the 8% divided by 2 squared minus 1, and you get 8.16%. So he's actually earning more than his contract says. Additionally, if this were the opposite, if he were paying a loan and interest was compounded more frequently than annually, he's actually paying more than he says, more than the contract says. And finally, m equals 4. The effective rate is equal to 1 plus the stated rate of 8% divided by the number of compounding periods raised to the number of compounding periods minus 1, and you get 8.24%. You can do this in your calculator. You don't have to use the equation. To do it in your calculator, you use the I conversion button, which is also the number 2 button. So you push second, I conversion. I conversion is number 2. You enter in your nominal rate is equal to 8%. Your compounding periods per year is 2. And you compute your effective. So your effective rate is equal to 8.16. And you can do this for each of the different options. In your graphing calculator, you push your apps button, your finance button, and you scroll down to effective. I'm pretty sure you enter in nominal comma compounding periods per year. So you would enter in 8,2, push enter, and you should get 8.16. I don't have a graphing calculator anymore, so I'm working from memory, but that should be accurate. You can always look it up in your calculator's manual. So to do this, you push second and your I conversion button, which is above the number 2. Let me clear this. To clear within a menu, you had to push second and clear work once you have it opened. So second and I conversion. Well, I guess that didn't work. Second and I conversion. We'll enter in our nominal rate. It's 8%, so 8 and enter. You push the down arrow. The up arrow. It asks for the compounding periods per year. So you enter in 2, enter the up arrow, and you push compute for your effective rate, and you get 8.16. So if we wanted to do this for quarterly, we would push second, I conversion, enter in our nominal rate, so 8, and enter. The up arrow, our compounding periods per year is 4, enter, up arrow, compute, and you get 8.24%. So you push second I conversion, which is the number 2 button, enter in nominal equals 8, enter, and the up arrow. Compounding periods per year, you would put number 2, enter, up arrow, and compute. And that would tell you the effective rate is 8.16. So what is the effective annual rate associated with a 10% nominal rate if interest is compounded daily? So M is equal to 365. We can use our formula. EFF and EAR are same thing. In your calculator, if you have a graphing calculator, it's going to say EFF. I'm pretty sure the financial calculator also says EFF. But it's 1 plus your stated rate over M raised to M minus 1. So if you were putting this into your calculator using the equation, the EFF would be equal to 1 plus the stated rate, 10%, divided by the number of compounding periods per year, 365, raised to 365 minus 1. And you would get 10.52. Alternatively, you could use the I conversion button. So you push second, I conversion, nominal equals 10, enter it as a whole number, enter, up arrow, compounding periods per year equals 365, enter, up arrow, compute, and it will say the effective rate is equal to 10.52. Oops. So here with our calculator, you push second and I conversion. Your nominal rate is 10. Enter, up arrow, compounding periods per year is 365. Enter, up arrow, and compute. And you get 10.52%. So here's just a fun little thing to do. Looking at how fair is checking to cash. You know, one of those will give you a payday loan. It's a payday loan is a small unsecured short-term loan. It usually ranges between $100 and $1,000. So here a borrower that borrows $100 and keeps it for 10 weeks. So that's 5 2-week periods, would have $75 in fees. So they would be paying $15 every 2 weeks, or 15% every period. So $15 is 15% of $100. So the nominal rate, 15% times 26 2-week periods, is 390%. The effective rate, here we have 1 plus our nominal rate, so our 390% divided by 26, raised to the 26th power, is 3,785%. So if a person got a $100 payday loan and kept it for 26 2-week periods, so 52 weeks, 1 year, at the end of that year, they would owe $3,785.67. You can put this in your calculator if you don't believe me. The present value, they deposited $100, or they got a loan for $100. N is 26 2-week periods. The interest rate, the nominal rate divided by the number of compounding periods, so it's 15%. And the payment is 0. Then the future value is $3,785.68. Pretty impressive. So next we're going to look at payments. So what payment do we need to make to have enough saved up in the future? To have a certain dollar amount saved up in the future. To calculate this, it's equal to the future value, the amount we want to have saved, divided by 1 plus the stated rate raised to the nth power minus 1 divided by the stated rate. So here's an example. You want to buy a house in 5 years. You estimate the down payment is $30,000. To get this $30,000, you want to make annual end-of-year deposits into an account that pays annual interest of 6%. So at time period 0, we have nothing. We're wanting to save money for 5 years. And at the end of 5 years, we want to have $30,000. We want to know how much we have to deposit every year for 5 years to have $30,000 if our interest rate is 6%. So N is equal to 5. Our interest rate is 6. Our future value is $30,000. And our present value is 0. We have nothing saved now. We want to have $30,000 in the future. So let's clear all of this and clear our time value of money. N is 5. The interest rate is 6. The present value is 0. And the future value is $30,000. And we want to compute our payment. So we're wanting to deposit into an account $5,321.89 every year for 5 years, earning 6%, to have $30,000. So how did I know that we were solving for payment here? Remember, we use the payment button whenever it's equal recurring cash flows. So these cash flows occur at equal points in time over a specific period of time. And the cash flows are going to be equal. We want to make equal annual end-of-year deposits. So I know that we want to solve for payment. So now that we know how to solve for payments, we can do loan amortization. So loan amortization is the determination of the equal periodic loan payments to provide the lender with the specific interest and to repay the loan principal over a specific period of time. And we can develop a loan amortization schedule, which shows where the interest and where the principal is going. To calculate the equal periodic loan payments, we can do this by using this equation. The present value times the stated rate divided by 1 minus 1 divided by 1 plus the stated rate raised to the nth power. Or we could put it into our time value of money. So let's say you borrow $6,000 at 10%. You're going to make equal annual end-of-year payments for 4 years. To find the size of the payments, the lender determines the amount of a 4-year annuity discounted at 10% has a present value of $6,000. A Basically, all that says is you're borrowing $6,000. So at time period 0, you're receiving $6,000. At the end of 4 years, you want to have that balance down to 0. The lender charges 10%. So we want to know how much we have to pay every period to have our balance 0 at the end of 4 years. So N is 4. The interest rate is 10. The present value is $6,000. The future value is 0. Again, I know that we need to solve for payments here because these are equal periodic cash flows. So first step is to clear your time value of money. N is 4. The interest rate is 10. The present value is $6,000. You've received $6,000, so positive. The future value is 0, and we want to compute our payment. So we have to pay $1,892.82 every year for 4 years to have this repaid in 4 years. So we can create a loan amortization schedule now that we know our payment. We have our years, 1, 2, 3, and 4. We have our beginning principal. We've borrowed $6,000. We have our payment, $1,892.82. We have the interest, which is 10% times our beginning principal, which we'll label number 1. So 10% times $6,000 is $600. The amount that goes towards principal, columns 2, columns 3, column 4, would be column 2 minus column 3. The payment minus the interest is the amount going towards principal. So $1,892.82 minus $600 leaves you $1,292.82. And so that gives you your ending principal. Which would be column 1 minus column 4. So $6,000 minus $1,292.82 leaves you with a principal of $4,707.18. The ending principal in year 1 is your beginning principal for year 2. So $4,701.18. Our payment stays the same. Our interest now is 10% times $4,701.18. So our interest is $470.72. The principal is the payment minus the amount going towards interest, so the $1,892.82 minus $470.72. So $1,422.10. Our ending principal is our beginning principal minus the amount of the payment that went towards principal. So $4,701.18 minus $1,422.10 leaves you with $3,285.08. Your ending principal becomes your beginning principal in year 3. Your payment's the same. Your interest is 10% times $3,285.08. to give you $328.51. The amount that goes towards principal is your payment of $1,892.82 minus the amount going towards interest of $328.51 to give you $1,564.31. To get your ending principal balance, it's your beginning minus your amount towards principal for that period. So $3,285 minus $1,564. That gives you $1,721.77. And that becomes your beginning principal. Your payment stays the same. The amount of interest that you're paying is $1,721.77 times 10%, so $172.08. The amount that goes towards principal is the loan payment minus the amount going towards interest, so $1,720.74. So your principal here is, this is supposed to be 1,720, excuse me. The difference here is 3 cents, and that's due to rounding, but it shows how your payments go towards interest and principal every period. So the amount that you're paying towards interest every period is decreasing, and the amount that you're paying towards principal every period is increasing. So we can also find growth rates or interest rates. So we've solved for everything else on our calculator, so we can do this too. To find the interest rate using the equation, it's the future value divided by the present value, raised to 1 over the nth power, minus 1. Or you can put it in your calculator. So Ray purchased an investment 4 years ago for $1,250. It's now worth $1,520. So what rate has he earned on this investment? We can put it on a timeline. At time period 0, he spent $1,250. At time period 4, it's worth $1,520. So what rate did he earn? We could use the equation. The interest rate is equal to the future value 1,520 divided by the present value 1,250 raised to 1 over n, which is 4, minus 1, and you get 5.01%. He earned 5.01% per year. Alternatively, you can put it in your calculator. The present value is a negative 1,250. The future value is a positive 1,520. Remember your negatives and positive signs. N is equal to 4, and the payment is 0. So what is your interest rate? First, clear your time value of money. The present value is a negative 1,250. The future value is 1,520. N is 4, and the payment is 0. So we compute the interest rate. And you get 5.01%. Here's another example. Jan can borrow $2,000. It will be repaid in equal end-of-year payments of $514.14 for 5 years. She wants to find out the interest rate on this loan. So she's going to receive $2,000 now. She's going to have that paid off at the end of the period, 5. And she's going to be making payments of $514.14. Now I would put these in as negative because they're money leaving her pocket. So the future value here is 0, but you still have to make a payment in the 5th month or the 5th year. So n is equal to 5. We're wanting to solve for the interest rate. The present value is $2,000. Future value is 0. And the payment here, remember, equal periodic cash flows. The negative $514.14. So we can solve for the interest rate. So clear your time value of money. N is 5. Present value is $2,000. Future value is 0. And she's making payments of $514.14. Put that as a negative and compute the interest rate. And you get 9%. So we already solved for n when we were talking about time to double. But sometimes we are interested in solving for the number of time periods it takes for a cash flow to grow to a certain amount. So Anne wants to determine the number of years it will take for her initial $1,000 deposit to grow to $2,500. She's earning 8%. So we put this on a timeline. So she's depositing $1,000, and at some point in the future, she's wanting to withdraw $2,500. So we're wanting to know how many years, and the interest rate is 8%. So the present value is a negative $1,000. We don't know n. The future value is $2,500, and the interest rate is 8. The payment is 0. So we need to solve for n. So clear your time value of money. The present value is a negative $1,000. The future value is a positive $2,500. Payment is 0, and interest rate is 8. And we compute n. And you get 11.91 years. 11.91 periods. Here we're talking about annual compounding, so it would be years. So here's another example. Bill can borrow $25,000 at 11% interest. He's making equal end-of-year payments of $4,800. He wants to see how long it's going to take to repay his loan. So at time period 0, he receives $25,000. He's making payments of $4,800. So these would be negative. And he's wanting to see how long it takes to have that balance down to 0. And the interest rate is 11%. The present value is a positive $25,000. Future value is 0. Payment is a negative $4,800. I know it's a payment because it's equal periodic cash flows. And the interest rate is 11. So we're wanting to solve for n. So clear your time value of money. $25,000. for the present value. Future value is 0. Payment is a negative $4,800. The interest rate is 11. So compute N. And you get 8.15 years. So that's it for this chapter.